So hello everybody, welcome back to my channel. This is Kshitij, and on this channel we talk about robotics, research and academia. In this eighth lecture today, we have a guest lecture with us, and he'll be talking to us about ROS, which stands for the Robot Operating System. So as always, we'll be going through a quick recap of what we have studied so far, a brief introduction about our guest of the day, and then the scope of the lecture is learning all about what ROS is, who can use it, why benefit from ROS, what are the advantages if you try to use ROS, and the other ancillary tools that come with it if you decide to use ROS eventually. So far we have looked into various kinds of sensing mechanisms, perception strategies, that is how the robot converts the raw sensor data and makes some sense out of it. And in the last lecture, we looked into various sorts of recursive state estimation, such as filtering methods and so on. In today's lecture, we want to see how these things come together for a robot to be able to move around in an environment. In essence, we want to see these things in action. So our guest of the day is going to introduce us to ROS, which stands for the Robot Operating System. And thus far, it had version 1.0, and recently there is a ROS 2 out as well. So we'll be discussing both versions in this lecture. So about our guest today, we have with us Sakshay. So hi, Sakshay. And he's an undergraduate student in computer science, and he makes videos on robotics and artificial intelligence. He has done projects in ROS, and even one of them was selected for the lightning talk at ROS World 2020. So he's the right person to teach us about ROS. All right, Sakshay, with that, I hand the stage over to you. So take it away from here.
So thank you for the introduction, Kshitij. So hello everyone, I'm Sakshay, and today we are going to talk about what is ROS, why should we use ROS, and its various different concepts and tools. So what is ROS? So people define ROS in various different ways. Some say it is a middleware, some say it is a framework to build robot software, and some say it is a meta operating system. For a beginner level introduction, we can say that ROS is a framework to build robot software. The robot software can be of varying complexity. It can be even be as a low-level controller, like integrating different devices or sensors. And it can take the data and also be used to build high-level software like path planning, perception, controlling, localization, and so on. So ROS actually stands for Robot Operating System. But as its name suggests, ROS is not an actual operating system. It is actually a set of software that runs on top of a Linux-based computer. But for a robot or a computer, it provides many capabilities like hardware abstraction, low-level device control, message passing, and package management, which are also the functions that an operating system provides us. And that's why it is called an operating system, but it is not an operating system as in general. So in order to understand what is ROS, let us consider an example application. As we can see over here, we have an image of an Amazon Prime robot that has to deliver some package from the warehouse of the Amazon to a customer. So we can consider this robot delivery task. Now, this robot delivery task can be broken down into many different subtasks. If we ask a fellow human being or just a colleague co-worker to go and deliver some groceries from, let's say, from one place to another, it is as simple as giving him the address and asking him to go over there. But for a robot, this task actually boils down into various different subtasks. As soon as we provide the robot with some address, the robot needs to plan its path starting from where it is to the address that we have provided it. Then it has to start its motion, and while going, it has to do a lot of intermediary motion planning. It has also to avoid the different pedestrians that are moving across it and from its front. It also has to decide what is going to be the speed that the robot has to maintain in order to reach at a particular time or particular location. So these different subtasks can be organized into, let's say, perception, motion planning, and control. And ROS provides these different subtasks as packages. This makes ROS a modular and reusable format. Modular in the sense we can easily remove one part and replace it with an improved part. For instance, if we improve the perception algorithm, we can simply remove that perception algorithm and replace it with a newer one without actually changing a lot of different software here and there. And the packages that are provided are also reusable. This means that we can use the same set of software that we were using on, let's say, this Amazon Prime robot on some other robot that also has to do some similar kind of task. So it is also scalable. So we can, the solution that we used for one robot can be deployed on various different robots. So why should we use Ros? One particular example in that we discussed, Ros provides packages. One such use case of Ros is that. Another really good advantage of using Ros is it is an open source software. So various people can come and contribute to the open source and improve the software. Along with that, Ros also has a really good community support. A lot of people use Ros to build robots. Any problem that we face might have been faced by some other person in the past, and solution to that problem would have been provided by him on the internet somewhere. Ros has a community support website also, which we are going to discuss towards the end of this lecture as well. And since Ros is so popular, most of the robotics companies also develop their robots using Ros. This means that most of the robots and sensors that these companies develop are mostly compatible with Ros. For instance, various robots that have been used in space exploration, which use Ros as such. NVIDIA is also experimenting really hard with Ros to develop really good robots in general. So there is lot of research that is going on that uses Ros in their robots. Since Ros uses general concepts, they can be applied to various different robots. Now, the same robot that was sent to Mars is similar in concept related terms to a robot that will be running on Earth. Not only these mobile robots, there are other types of robots as well that use these basic general concepts so that we can make Ros compatible with all these different robots. Okay, so there are other similar systems like Ros as well that have come up in the past. One such is Microsoft Robotics Developer Studio. It was a robot software development framework that was developed by Microsoft, but it was discontinued in 2012. Another software development platform is Evolution Robotics Software Platform. It was developed by the iRobot company and was mostly used to program mobile robots. Another such software development framework was Nowkey. Nowkey, the problem with Nowkey is that it is only available for development of the Now robot. And we have a robot operating system developed by Open Robotics. This framework, as we know, is compatible with a lot of different robots and therefore has stood out the most from other similar systems that have been developed in the past. And that is also why we are going to discuss this in this lecture. Okay, so the Ros concepts can be understood from this really simple example that we can see over here. In this image, we can see that there is a tree that is present in the garden, and on that tree, the tree has different branches, and on those trees there are various birds that are sitting and chirping and communicating with each other. Through this simple observation, we can understand the various different Ros concepts that Ros uses. So the first two concepts that we can discuss are publisher and subscriber. Now consider a bird that is sitting on one branch and wants to communicate with a bird that is sitting on another branch. So a bird that will be sending some messages or chirping will be sent as messages to the other bird that is listening to it. So the bird that is sending those messages is called publisher, and the bird that is listening to those messages are called subscribers. Now this particular message format that they are using, now the language of the birds is going to be called messages. And topic is going to be the actual messages that are going to be delivered from one bird to the other. So these two publisher and subscriber birds are communicating with each other through messages, and those messages are actually topics that are being sent. So the next two Ros concepts are service and action. So let us consider the two birds in one particular scenario. One bird asks the other bird to do some task. So the bird kind of keeps waiting for the other bird to do the task, and whenever it receives a message from the other bird that it has completed a task, it will continue its other work that it was doing. So such synchronous communication functions that are performed by ROS are called services. So in a software term, we would say that one part of the code stops for the other part of the code to execute. Once the other part has executed, it will come back and resume its execution in the original part of the code. A very similar concept to that is of actions. However, actions perform asynchronous communication. Now, in asynchronous communication, the original part of code does not need to stop for the other code to complete its execution. It will simply ask the other piece of code to do some work and keep on doing its own tasks. Now, services and actions are a bit of an advanced kind of mechanism in ROS. Therefore, these are not mostly used, but majorly used ones are publishers and subscribers. These services and actions are mostly used for some particular task that we want to perform in ROS. So the next ROS concept is node and edges. Now, in this tree example that we see over here, the different branches can be considered as ROS nodes. So a particular branch can have many different birds that are sitting on each of the different branch. Now, each of the bird is performing a publishing and subscribing task, or either of the birds are performing a service or an action-based task. So each of the different nodes is actually performing publisher and subscriber, both of these tasks. Relating to that, we can define a node as an independent process that is performing some computation. So just like a branch has many different birds, a node has many different set of publishers and subscribers that it can perform its computation. Now, each of the different nodes that are present are connected by what are called edges. So in this, once again, coming to this example, if we have a particular bird that is sitting on a particular branch, and we have another bird that is sitting on another branch, and these two are communicating, then we will say that both these nodes over here are connected to themselves by edges. Edges form the connection between two nodes, which two nodes will be communicating with each other. Now, this collection of nodes and edges forms a mathematical based architecture called a graph. ROS is modeled using these nodes and edges that form what is called a ROS graph. As we can see in this image over here, there are various different nodes that are running for a robot, or these nodes are connected by edges, and the complete architecture of these nodes and edges is what is called a ROS graph. And the other concepts are Ros Parameter Server, a Ros Package, and a Ros Workspace. Coming back to the original example that we have, a Ros Parameter Server can be modeled like a DNA of the tree. Parameter Server provides parameters in such a way that we can change those parameters on the go whenever we are developing applications that need some parameter tuning as such. For instance, if we have a node that wants to use a variable, let's say k, we can define that variable k in a parameter server. Then on starting, that node can, during initialization, the node can take that value k from the parameter server and use that in its own computation. Then we have the concept of Ros Package. So similar to how a tree has a different branches, this complete tree can be modeled like what is called a Ros Package. A Ros Package is a collection of nodes that are similar in computation in some way or another. Like for a perception package, we can have different nodes, like one node for taking in an image, another node for processing that image, and some other node to process that image furthermore. So the set of related nodes constitute what is called a Ros package. Now, in a garden, we can see that there is not going to be a single tree, but there are going to be multiple trees that are present in a garden. So that garden that has multiple trees is what is called a Catkin Workspace. A Catkin Workspace is a development environment that has various different packages that are present in a particular workspace. Now, if we consider again the original example of robot delivery, we can have various different packages for navigation, motion planning, and so on. So in order to combine all these packages and develop them in a more easier way, we use what are called workspaces. So they provide a development environment where we can build and compile all the code that we have. So we have two particular terms over here, Catkin Workspace and Robot Workspace. Now, some people tend to confuse these two terms. So to clear this up, a robot workspace is the set of points that a robot can reach. So for a navigation example, if we consider a map, now in the map, wherever the robot can reach is what is called its workspace. Catkin Workspace actually provides an environment where we can build, execute, and organize the ROS code that we have. So these two terms are actually different. Catkin Workspace is a more software related terms and robot workspace is a more robotics related term. Okay, so now let's discuss some various different tools that are used for the ROS robot software development. The first and most important one is the RViz tool. RViz stands for ROS visualization. It is a really good debugging tool that is used for debugging the robot sensor values that it is receiving and the different algorithms that we develop. Two particular use cases that we can discuss are something like this. Here is a robot that is present over here, and we have a camera sensor that is attached to the robot. So whatever that camera is reading, we can see that in the RViz tool that we have over here. So in front of the robot, there is a cupboard, and that cupboard can be seen by the robot camera over here. Another example of where we use RViz is to visualize algorithms. Now, for instance, if we want to develop, let's say, the A-star algorithm for robot navigation, we can use RViz to visualize how the A-star algorithm is working and use it to debug the algorithm where we are committing any mistakes or where we are getting it right. So one particular thing to note about RViz is that it is not an actual simulation environment, and it hence does not allow any physics to be used as such. Another ROS tool that we have is Gazebo. Gazebo is an open source 3D robotic simulator. It is integrated into ROS using various different ROS packages. Now this Gazebo simulator is the actual physics simulator that is used in ROS. In order to simulate various different use cases of the robots, we use this Gazebo simulator. The other ROS tool that we have is the Rqt Graph. Now this Rqt Graph is used to visualize the ROS graph of an application. For instance, over here, we can see that there are various different nodes that are running, like the robot state publisher, the Turtlebot 3 drive. The connections between these nodes can be visualized using Rqt Graph. Now the Rqt Graph, the Gazebo, and the RViz, these three are actually really good tools that we can use to debug our robot software application that we have developed. In case like during development, if we have missed any node, we can use this Rqt Graph to check whether that node is present, whether that node is connected to the software, and what is the message that it is receiving. So these three tools are really useful for robot development. Another really interesting tool is Ros Bag. So Ros Bag is related to a concept we have called data-driven robotics. In data-driven robotics, robot applications are developed based on data. So Ros Bags actually provide that functionality to record the data that a robot generates. So there are, at any particular time, there are various different topics that are running, various different messages that are being transferred from one node to the other. Ros Bags help to record those messages and play back those messages whenever we want at any particular time as well. Like if we are working in a lab and we have a robot at a lab, we can use a Ros Bag to record all the different messages that robot was giving out. We can record that bag, save that bag, and take our laptop to our home. We can then run the Ros Bag again to simulate all the different messages that we had recorded when that robot was running in that lab. The next tool that we have is of launch files. So launch files help us to automate the execution of the different nodes. Now for a robot application, as we discussed, there may be various different nodes that are running. One node for perception, one node for motion planning, one node for control, and so on. Now we cannot start the execution of all these nodes simultaneously at once. In order to ease this process, we have what are called launch files. Using launch files, we automate the execution of nodes, and these launch files can also set the different parameters that can be that are used by different nodes. Also, we can use these launch files to launch other different launch files that are going to launch other different launch files or other different nodes. So launch files help in execution or automating the execution of the nodes. Next up, we have the different ROS packages that are used in robot development. Now, there are a lot of different packages that have been developed for ROS, big or small. But here we are only going to discuss some specific ROS packages that are relevant to mobile robotics. So ROS, one very important ROS packages of TF or transforms. Now, transforms package provides us with functionality to calculate the transforms between different frames of reference. Now, frames of reference is a very particularly important concept in robotics, where we need to calculate the transform between various different reference frames. For instance, one frame is present at the origin and the other frame is present on the robot. We can simply provide the reference frames to this transform package, and the transform package is going to compute the transform metrics from that origin to that robot transform frame. The TF package calculates static as well as dynamic transforms. Like from the origin to the robot, the transform can be calculated. And from the robot to the laser sensor, the transform can also be calculated. So it provides both of these transforms as such. The next ROS package that we have is of gmapping. Now, gmapping is a package used for mapping the environment. As we can see in this image over here, a robot can be used to build a map of its environment using this gmapping ROS package. So it provides the functionality of SLAM, simultaneous localization and mapping, to build a map of the environment. Uses the raw Blackwellized particle filter to generate those 2D grid maps. Next ROS package that we have is the AMCL. AMCL stands for Adaptive Monte Carlo Localization. This ROS package is used for localization of the robot in an environment. So these are the different ROS packages that we discuss in this lecture. There are many different packages that can be used, and like only for localization, there are many different packages that are available that use various different algorithms for localization. Similarly for mapping as well, there are different ROS packages that can be used. So ROS is a really powerful tool that we can use to build robot software, but it has its own shortcomings as well. So for the further improvement of ROS 2 was developed. The enhancements that ROS 2 provides over ROS are helping the development of multi-robot systems. It also helps develop the real-time systems. And ROS 1 had a particular drawback of not being secure. ROS 2 provides some security and encryption mechanism in the basic ROS environment as well. Also, ROS 2 is more production ready and more industry oriented compared to ROS 1. So we can develop robots faster using ROS 2. And to provide this maintainability, ROS 1 can also coexist with ROS 2 for a particular robot application. For instance, if we have an algorithm that only works in ROS 1, we can provide a bridge between ROS 1 and ROS 2 to run that same algorithm in ROS 1, but keeping ROS 2 running as well. So for corresponding to this lecture, we have also prepared a working example that the students can try, where the students can try to get a more hands-on experience of how ROS works and what is ROS. So we are going to be the environment that we have provides a Turtlebot 3 robot that will be simulated on the student's computer, and you would have to do certain different tasks that whose instructions have been provided in the GitHub link that we have in the description box below. You can also scan this QR code to go to that GitHub link and read those instructions. So for the step 1, the first step that you have to do is actually simulate the robot by running the different commands and use the tele operation to move the robot. So once you start that application, you would have to control the robot using your keyboard and move the robot around to see how the robot moves. The challenge we have for this step is, can you make the robot go in a spiral, as we can see in this image over here? For the second step, you would have to use the gmapping ROS package to create a map of the environment. All the instructions to run the gmapping node would be provided over there in the README of the complete project. Following that, you can run the gmapping algorithm. Then you have to move the robot around using your keyboard to map the environment that the robot is being simulated in. The challenge for this step would be to try making a complete well-defined map of the environment that would look something like this over here. So the third step would be to localize the robot on that map that we developed in the step 2 and navigate that map from a start to a goal point. The challenge for this step would be to make the robot, can you make the robot go from point A to point B? And as discussed before, all the instructions will be provided in the README of that project. So there is a pop quiz that following the instructions, now for the different steps that we were performing, we had to initialize various different nodes. Like for instance, the first node was simulating the robot. Second node was the teleoperation of the robot. An additional node that we required in step 2 was the G mapping node, and an additional node was the navigation node that we had to launch in order to simulate the robot. So the task or the pop quiz over here is, can you prepare a single launch file to start the nodes automatically? So launch files are used to automate the execution of nodes, and that this is what we would require you to do, to prepare a single launch file that starts all the nodes automatically. And Ros, as we discussed, Ros has a big community support. So whenever we are stuck at a problem, there is a high chance that some other person would also have been stuck on that problem and would have posted that solution on the internet online. So Ros Answers is one such website that we can use to search for different queries and questions related to our problem that we are facing with Ros. You can check this website out to see the different discussions that have been over there in that on that website. Okay, so this is what we had to discuss in this lecture. So thank you for listening.
All right, Sakshay, thanks so much for this amazing and well-detailed lecture. Also, I think having a worked example would make it easy for the students to get to grips of the concepts that I have been talking about in my previous lecture and what you presented in this lecture as well. I think the whole point of robotics is to have a whole hands-on approach, because you can read a whole lot about it in theory, but unless you have seen it in action, it doesn't make much sense to you. Before we wrap up, I just had a few kind of quick questions or sort of like queries that would likely arise when students start to do these exercises. So I'll just quickly discuss them with you. Maybe there would also be some clarifying points for the students as well, right? So we discussed that Ros has community support, right? But this worked example that we gave them is like a custom exercise dedicated to this course that we are running. So in case if a student has certain query, since the repository is hosted on GitHub, do they kind of make an issue on GitHub and then we go in and support them, or do they ask a question on the community forum instead and then hope that somebody gives them an answer? Like, where do they go in case if they are stuck with something?
So there are actually 3 places that a person can go to while performing this worked example. The first is the issue section as such. We can any student that is stuck can write their issue on that issues tab on GitHub, and we can help them over there. We can also use those Ros answers to provide us community support for the issue that they are stuck at. But waiting for community would be a little time consuming compared to putting an issue, since we would be active most of the time to help the students. Third way that we can have is the tutorials that we have, the worked example that we have developed is actually inspired from some other guide related to Turtlebot 3. The link to that would also be provided. So you can also check out that link to read more about what is the different process that actually is running behind the scenes. You can check that link as well. So I would recommend these 3 things so you can get help regarding any issue when you face while working on that worked example.
Okay, well, there are 2 additional resources that people could request. So one is, I also have a Discord community, so they could join that one. The link to that is already in the description and channel info as well. The other option is for quick queries that don't require multimedia attachments. There's always the comment section below the YouTube channel itself. So basically, as you can see, there are like multiple different channels for you to seek help. It's just about being proactive and trying to get the things done if you really want to learn about Ros, right? So on this note, there is also another thing that we could probably clarify at this point. So while the worked example, we have tried to keep it very basic and reduce the amount of reduce the focus from coding to more on the application side of ROS and robotics. In case if somebody wants to contribute a particular enhancement that they think would be really good for this repository and for future learners, would you be open to them making a pull request, and then we can evaluate how good that would be for contributing to the repository, and then have them integrate into the existing repo?
Yes, that would be really amazing to do so. One process that I have seen people following while contributing to open source repositories, and the students can follow as well. First, put an issue on the GitHub project regarding what they feel is missing and what they feel should be added, providing more description on that. Then we can after confirming that it is actually a good feature, or like some even suggest some improvements on that issue, and then that they are fully sufficient that how they need to perform that issue, then they can code their own example, add their own things, and pull and start a pull request on that repository.
Right.
So after we have done some checks that whether it is compatible with the original code, or well, there won't be many compatibility issues as such, but if once we have a look, we can then integrate their pull changes that they have made to our original, like the project as such.
Okay. All right. Those were really clarifying, because I think, every time we have thought about certain different aspects when preparing this repository as instructors, but as a student, when they get their hands dirty, maybe they come up with something that could be really useful for the rest of the community, right? And that's the beauty of doing these things open source. So one person may not see everything, but the other person might give us some nice feedback that might be beneficial for them, for us, and for the rest of the community learning from it, right? All right. So in closing, thanks so much, Sakshay, for joining this lecture series and contributing to introducing ROS to early stage learners, and giving them a detailed experience of what ROS could be like, and also a really nice immersive worked example for them to get their hands dirty. So in closing, as we always do, so pop quizzes, any questions and queries, we discuss multiple channels of how you could reach out to us. Be sure to subscribe to my channel, to Sakshay's channel. The link would be in the description box below. So be sure to subscribe to both our channels. And we hope you benefit from this lecture series, and share with other fellow learners who are interested in ROS and robotics, and are kind of struggling or clueless or looking to get started but don't know where to go and how to start. So these lecture series are being structured for specifically those kind of audience that want a structured approach. So hope you benefit from these kind of lectures. All right then, Sakshay, thanks so much for joining us, and see you guys next time. Take care.